today is the second day of the Nano conference here at Illinois. The session this morning is Bio and Nanotechnology and Nanomedicine. My name is Paul Kenis. I'm the chair for this session. My appointment is in chemical and biomolecular engineering. Let's immediately start with the first speaker, who's Dr. Bosoon, who's from the United States Department of Agriculture. And he's going to talk about applied nanotechnology for foodborne pathogen and toxin detection.
Thank you for time introducing, and then thank you again for inviting me to have this kind of wonderful opportunity. I'm actually the research scientist in USDA ARS. USDA is a very big federal agency, but ARS is one of them. I'm going to very brief introduction is who we are. This is actually US map, actually, you know that. We have 8 different agencies nationwide from East Coast to the West Coast. Okay? And we located Athens, it's about 50 miles from Atlanta to the east. And we have a very close to campus, University of Georgia. So we're also working very closely, working in collaboration with the University of Georgia people. And then my mission actually to be here, not only just to present what we are doing, and also I will get some good networking and that you in faculty in Illinois, because I know that you have very advanced technology here in terms of nanotechnology. Okay, so today I'm going to show very brief what we are doing. Our research is most applied. My personal research is actually working on the food safety. So I'm trying to develop some new technology like nano to solve the problem. Okay. And in terms of nanotechnology research, we have a very limited number of people working on that. Okay? So actually we have 6 different locations who are working the nanotechnology. 2 of these are Winmore from in Pennsylvania, and 2 groups working the Albany in California. Okay? And recently also some scientists working in New Orleans. I'm a person from Athens. Okay? All right, very brief. The ARS, I don't know how many people is familiar with the ARS, but the ARS is one of USDA, the agency, but we call it in-house research institution. So we have actually 100% research from the Congress budget. So we actually about 2,100 people, scientists, with more than 6,000 employees supporting scientists and the technicians. So about 8,000 people working to solve the agriculture problem. Okay, so we have actually 100 different research locations in nationwide, including a couple of some overseas, France, Argentina, Australia, and China. Okay, we actually used 1.1 billion is our budget, but now it's budget, as you know, it's a cut. I don't know the current budget, but it's around 1 billion is our budget. Okay, all right. We operated under the national program, so this is very unique and also very good system in terms of research management. Okay, we have actually the 1,000 research projects every year under 20 national programs. Okay, so we have a national program leader who manage, who organize all the research in the nationwide in the world. One of that, actually we have 4 different categories in terms of the research. So I'm working under the food safety. Okay, so we have a national program leader on the food safety. Today I'm going to share our research. Actually, I'm going to show the 3 or 4 different research we are working on. And one of them is a biofunctionalized nanorod, and second is a molecular imaging to detect the single molecule, in this case, in the food toxin. So we are still working on the detect of food glycine from the capsule. Okay? Some of that is a proof of concept still, but we try to apply this technology to solve real problem using the food matrix. So it's not, it's still on the way. We will not get any final result yet. So that's the reason I want to learn some more new technology we develop to implement it to our program. And finally, and also we developed a hyperspectral microscope imaging. So I'm going to share very brief information. What is advantage of this technology in terms of applied nanotechnology? Okay. All right. As you already know, this is actually how nanotechnology initiative has started about 10 years ago, 2001. And that time is a national, the federal agency, the 8 agencies started, including NSF. So maybe I think CNSD is about starting with that time, right? Year after USDA joined, okay? And it's called the NIFA. So previously NIFA is a CSRES. This is actually the funding agency to support the funding to the most likely state university. But NIFA is actually our sister agency under the REE, but we are working the 100% research, in-house research. NIFA is 100% funding. Okay? So now actually more than 25 federal agencies participating in the National Nanotechnology Initiative. That means there are lots of area, many different areas applies the nanotechnology. So maybe I think you can find out what they're exactly doing through to their website, and then you can find it easily. Okay? Again, yes, today I'm going to share my current research in the conducting the Russell Research Center located in Athens, and the biofunctionalized nanorod, how we can use this technology to detect food pathogen, and molecular imaging, how we detect some toxin in the single molecule level. And also we are working, I talked to yesterday one of the faculty here, he also working the SIRS. So we're trying to apply the SIRS technology to detect foodborne pathogen. So in that case, we just collect the pathogen from the chicken rings, okay? Because the Georgia is actually the #1 chicken capital in the nation. So we have a lot of chicken industry around. So they want us to solve the problem. So I'm going to show why we need to develop this technology. Finally, the hyperspectral microscope. Many of you, all of you heard about food safety outbreak every year. About the summertime, there's a big USA Today or even the ABC, CBS News, there's some outbreak happened. So this is actually history of the many, several years. But this is most recently, as of 2010, this is based on the CDC. We just spend almost $152 billion per year in terms of food safety. Okay? There are many people who are sick, even if they die, and also more than 17,000. This is already confirmed. Okay? So I guess it's more than this number is happening. So they just actually got all the data and then compile it to summarize most infection and incidence cases is more than 15%. Okay, followed by the Campylobacter. Those two, the strain is highly affected by the poultry and egg. That's the reason our research is focused on poultry and egg to detect, not just detect, early detect, rapidly detect. Because as you know, the outbreak that happens today, if we don't see what's happening exactly, they spread out in the 25 state next day, and the following day is in 50 states already got people sick. Okay? So that's the reason early detect, rapid detect is very, very important in terms of the food safety. And especially for meat and poultry egg. So we actually work in the USDA to take care of meat and poultry and egg. FDA to take care of fruits and vegetables. So there's actually different safety in terms of the safety inspection. So in that case, how many heard about STAC, cigatoxin? Okay, STAC was new. It's not new in state, but especially Europe. You heard about some people that got, I think almost 50 people died in Germany, got a bean sprout. That's STAC. So many of us understand just 0157H7. It's the most common E. coli. However, another E. coli got people sick. So that's the reason we work on the STAC now. And Salmonella, Campi, monocytogenes, that's most important the pathogen we need to detect. Okay, what's happening? What is current detection method? There are many detection methods available commercially. Okay. However, those methods, one of them is the ISO method and fluorescent method, and now is I think the more immunological and the biochemical methods people using, such as ELISA and the PCR. But those methods is sometimes it's working well, but they sometimes not well. So in most cases, so we just consider time consuming. I told you in the outbreak we have to develop some rapid and early detection is very critical, right? But in that case, it's a time consuming and cumbersome. Result is sometimes work, sometimes not. Also, the sensitivity issues, detection limit. So some technology, for example, ELISA PCR is working well, but they don't differentiate a live versus a dead cell. So there's another challenge. How can detect a viable cell instead of a dead cell? This is a very important issue on the sanitation in terms of sanitation or sterilization on the food processing line. Okay? But this is a current method that we are practicing now. USDA Food Safety Inspection Service, and they're doing all of this. I'm not going to read everything, but the only thing I want to read there, if they find the final confirmation what exactly that pathogen is, it takes about at least a week, sometimes more than 2 weeks, confirming process. And look at the cost. Each sample, it costs about $100. It's a very expensive method as well. Okay? So now we're just developing nanotechnology to solve this problem. So one of them is a biofunctionalized nanorod. And every detail is already published in Nanotechnology journal, so you can read there. And this is what it is. We just made a nanorod using this silicon and gold composite. And then we just, basically this technology enhanced the signal. So that means even though we have a very small number of the target, we can detect. So that means we can much improve limited detection. Okay? And this is actually the nanorod fabrication process. I'm going to explain detail. Again, this is already published. And this is actually how we can optimize to attach a gold particle in the nanorod and how we can attach our marker to separate. So this is actually also studied optimization. All right, this is good, very promising. So we applied to detect the salmonella. So in that case, we can see the single cell the salmonella as well. Okay. Of course, this is a very delicate process, so we consider how we can make this one is a more real situation. We're still working on developing this technology. And next, second research I talked about the molecular imaging. This is single molecular detection, basically in this case in the ricin. So we just started the proof concept using the atomic force microscope, how we can see those kinds of target molecule. So we actually, this is very small molecule which has an A and B chain is for about only 64 kilodalton, so small molecule. So this is actually the protocol here. So substrate modified, we just immobilized in our target molecule, in this case of ricin, and also we just modify the AFMP. So in that case, we attach either the antibody or aptamer. So we start with the antibody first, and we already got publication in the Nature 2009. And then we just detect and create topographic image as well as a recognition image in that case. So as you see, this is actually the molecule on the chain A, chain B. The shape is finished. So that means we could detect a single molecule with the AFM. Okay. And we just apply the field sample amount is 1 nanogram per mil. And this is actually the topography, and this is a recognition. So as you see, the previous slide, we can match this molecule model. And also, we just after we just proved using the antibody, now we're working on using the aptamer. So maybe, I think it's aptamer. You know that many of you know already that it's very efficiency we can make easily and very stable. So we're using actually DNA aptamer in terms of stability. And you also can see the very detailed our target with the ricin using the aptamer. Okay? And also we just working on some of the simulation with this aptamer binding, how this binding part is located. So this is very important in terms of the real application. So we just working on this simulation part and just published the journal last month issues. And this is actually found 9 different patterns. So I think most of them is one of these. So this is very important when we design the new sensor and the chip, something like that. And also we compare the binding force. This is also another important issue. even though I think they're using the aptamer, the binding force is very similar, even better than the antibody. So we just prove this phenomenon. And the third application is actually surface enhanced Raman. So also we're using the surface enhanced Raman substrate with a silver nanorod. And in that case, you can see the different pattern from two different tests. This is Salmonella type murium. This one is E. coli, 157H7. And this is actually show the immobilize our target E. coli with the nanorod. So the signal is changes. So based on the signal, we just detected something. Okay, this is one promising. I told you something that the ELISA PCR, we cannot differentiate the live versus dead cell, right? So we can see there's some different signal from live dead cell. So we just maybe apply to this technology, continue work to differentiate the some viability of the pathogen. And another thing is we're working on the biopolymer based. This is actually silver encapsulated with the biopolymer. The reason we use the biopolymer is more stable and the shelf life is longer. So we're just working in this area as well. And we just compare how long we can stay our biopolymer encapsulated the silver. So we highlighted this technology just last month. We have Agriculture Research Magazine. If you go to the website of ARA, they have explained very well what this technology is. This is at the TM. We measure, we compare different colloid, the size. Some region, the 52 nanometer is working better than the other one. So we just still working on why. And this is another research we have. And the potential of this technology, we also trying to develop some kind of new method to improve our detection of limit, okay, detection limit. So in that case, 10 to the 9, this is most high concentration usually we start with. So 10 to the 2 is already challenged, is most biosensor arena. So we could detect the 10 to the 2. Of course, this is, we did not measure many samples yet, so we just continue to work to confirm this signal still the repeatable. Okay, just show us some possibility whether we could use this technology for our biosensor. Lastly, we are also working on the hyperspectral microscope using the first optical tunnel filter. The reason to develop this one, I'm going to show this. Okay. This is a petri dish most microbiologists are working on. When you look at this row and this one, okay, for example, this is E. coli, exactly same isolate from the chicken meat. If we grow the different arbor, they grow the differently. Okay? Okay, this one. This is a BGS. This is a BGS. If you have a different bacteria, for example, this is a Salmonella type murium, this is an E. coli, grows completely different. Okay, this is the reason it's very challenging the microbiologists to figure what actually this strain really is. Okay? Or we just doing some replicate, the result is different. And of course, time, when you look at this kind of pathogen grow here, you have to wait at least 24 hours, at least. Sometimes, as then, if you see the compound there, not compound, this is presumptive test, you have to go to wait another 24 hours. That means 48 hours. Then you can see this kind of salmonella, not Pathogen compound. So that's the reason people working in the PCR to confirm this strain. So we're actually working on the, this is a rainbow agar, just to grow the 6 different aspects. And this is a 24-hour drone, so the hyperspectral microscope research, we try to measure microcolony. Even I think before the 12-hour, even 6 hour, we can just scoop a very small tiny sample and then look at the spectrum. So our hypothesis, the spectrum should be same or minimal change. So if that works, we can detect this one very early. Okay? And this is actually how the hyperspectral microscope works. And we actually measure 450 to the 800, 89 different spectra. So we can see this is also the dark field illumination, especially designed lighting source, not just regular microscope. Okay? And this is what it looks like. So we just compare 6 different aspects. The pattern looks like similar. However, we just apply the different some metrics, some mathematical model, so we could differentiate. Especially 045, we can find almost 90% high accuracy. Some of them are still very challenging. Again, this is actual sample from food matrix. There's another reason it's very, very challenging. So we're still developing this technology, the work to apply the real food matrix sample. And in summary, this is actually the summarized. I already mentioned about it. So I think the time is running. So I'm going to stop here. Also, this is our research group and our ARS research group here, and this is my collaborator. So hopefully, I think your name is in the next time. Collaborator. Okay. This is actually in different agencies the funding for this particular research. Thank you for attention.
Quick question, yes?
So do you have afternoon against license? Is that
Yes.
where did you get them? Did you develop them yourself?
Good question. Initially, I think we still we just try to make our own with the PCR, the selects, but IPT they sell, and we just identify the ethno sequence, and then they just made it for us. Yes.
I also have a question. First, lots of people in academia and international are developing all kinds of technologies for sensing. What does it take to get from a proof of principle to an actual test that's being used on a widespread basis? So how long before we see some of these tests actually being used?
Some of them, most of them is already somebody that developed the proof of concept. For example, the first the biofunctional like the nanorods, the faculty in the Georgia, the physics department, he developed that nanorod. He's looking for the applied application. So I met him in a workshop like that, and I just explained my work, and then, oh, this is a good chance to work together. So that's actually start, and that's the reason I want to listen to some other people's presentation. I know the problem area, but you know the technology, so we just put together and solve the problem.
Good, wonderful. Thank you very much.